Let's look at part-of-speech tagging for natural language processing. We'll start with a quote from Gemini. Part-of-speech tagging, often abbreviated as POS tagging, acts like a linguistic passport for words in a sentence. It assigns grammatical labels like noun, verb, adjective, or adverb to each word. This helps computers understand the structure and meaning of a sentence. By knowing a word's part of speech, a machine translation model can translate it more accurately, or a sentiment analysis tool can determine if a sentence expresses positive or negative emotions. In the example graphic, we see here a sentence, "I like cats." In this sentence, each word is tagged with its part of speech. I is tagged with PRP, which stands for personal pronoun. Like is tagged with VBP, which stands for first person singular verb. And cats is tagged with NNS, which stands for plural common noun. So we see the goal of part of speech tagging is to label each part of a sequence with its grammar form. Languages are made up of words, symbols, and the rules for constructing sequences. These define a language's grammar. Within a language, we have classes of words or categories of words, and these are sets of words that can be either relatively static, meaning they are unchanging over time, or there can be dynamic sets of words where new words are added and unused words are retired or maybe even removed from the word set. Some examples of these word classes in the English language include for closed or static word classes, which are relatively fixed sets of words, we have articles, pronouns, and prepositions. For open dynamic word classes, and these are changing word sets, we have things like nouns, verbs, and adjectives, and so on. An example of this we can see in the September 2023 update to the Merriam-Webster Dictionary, where 690 new words were added to the English dictionary. I've linked to the article here, and we can see this article that overviews just some of the 690 recent additions. And if we scroll through these, we'll see a lot of slang and informal words that were added. So this is the type of word that does get changed over time. And you'll see that these are nouns, verbs, and adjectives. So they all fall into those dynamic word categories. Another category we see here is abbreviations. So abbreviations are added. Those change over time. And then, of course, the digital world. The digital world is constantly adding new words to our vocabulary. Right at the top, we see generative AI, and so that is a new word that was added to the dictionary. And we heard from a generative AI, Gemini, in the quote read earlier in this recording. Large language model, which is also related to natural language processing, is on the list along with other words. So if you scroll down the word list, you'll see nouns and verbs that have been added to the dictionary. So these are all part of the word sets in the English language that are dynamic. The next question we want to answer is, so how do we do this part of speech tagging? And we'll start by looking at the Penn Tree Bank. So the English language Penn Tree Bank is a corpus and is one of the most known and used corpus for the evaluation of models for sequence labeling. The first link here is a link to the original publication that discusses building a large annotated corpus of English, which resulted in the Penn Tree Bank. This was published in 1993. In Papers with Code, the second link, we see publications that reference the Penn Tree Bank. we'll take a look at that. If you haven't been to Papers with Code, this is a good resource for finding papers, seeing papers that relate to this paper, used to this paper, and used the code or the data associated with the paper, which you can also find here at paperswithcode.com. You'll see on the right usage, a usage chart over the last few years, some training benchmarks using the data set and the models that were used to create those benchmarks. And then you see papers that reference this data set. And it looks like we have quite a lot of papers here. We can sort them based on the dates. And you'll see the first paper referencing this was from 2004. Sorting the other direction, the most recent one, June 2024. So this data set has been widely used, 981 papers, and that's just what's listed here, which is certainly not necessarily going to encompass all of them. There are specific data set loaders that have been created to load this data set, and you can find these here as well. Within the Penn Treebank data set, there is a part of speech tag set. And so when we looked at these tags with I Like Cats, the PRP, VBP, and NNS part of speech tags, those are defined in the Penn Treebank part of speech tag set. A table of all the tags in that tag set is here, and you can see for each row we have the tag, a description of the tag, and just a few examples of words or symbols that fall within that tag. So CC is a coordinating conjunction, and examples that fall in that group are for, and nor. CD, a cardinal number with examples 1, 3, million. DT, a determiner, examples A and B, and so on. We scroll down further. We can see there are a lot of different parts of speech that are captured within this set. And you see PRP, personal pronoun. This was in our I Like Cats example. I was a personal pronoun. Scrolling through this, you see multiple forms of adverbs. You see a symbol tag, which is used to capture symbols in the language that are non-word characters. Scrolling down, we see all of our verb forms. So the base form of a verb, past tense, present participle, past participle, first person singular present, third person singular present, and then some examples that line up. If you remember our I Like Cats example, VBP was verb first person singular present. Like was tagged with that. And these examples line up. So the base form of the verb run has the past tense ran, the present participle running, past participle had run, first person singular I run, third person singular he runs. So you can see examples of the types of verbs in the English language grammar. You also see a special category here for sentence punctuation. So sentence punctuation has its own tag, and that is going to be separate from symbol. So symbol is going to contain symbols that are not punctuation. And we want to look at ways that we can generate these tags. In the first example here, I use the Natural Language Toolkit in Python and wrote a very small script to demonstrate using NLTK to generate part of speech tagging. So there's a link to the NLTK tag package in the docs here for Python. You see the submodules within this package. And in this brief script from NLTK tag, we import POS tag sense because we want to tag sentences in this example. We also use NLTK's tokenize to tokenize words and sentences in our example. And the example starts with 3 sentences. So this is a text that contains 3 sentences. In this case, the sentences are all quotes from movies related to AI. So we have the sentences, all programs have a desire to be useful. If a machine can learn the value of human life, maybe we can too. We marveled at our own magnificence as we gave birth to AI. So imagine this string of sentences. So this text string is text that you have read in from a document, and now you want to tag all of the parts of that text. So since we have a single string, the first thing we're going to do is tokenize that string using a sentence tokenizer from NLTK. And that gives us a list of sentences. And then for each sentence in that list, we are going to tokenize the words in that sentence. And then we are going to call POS tag sense from the NLTK library on that new list of word tokens and get the tags, and then we simply iterate through them and print them out. So you can copy this code and run it yourself and see what the output of that looks like. We'll look at some more code in a minute where I have the output on the web page. There are different types of POS taggers. There are rule-based taggers, which rely on a predefined set of rules. Statistical taggers use statistical models trained on large data sets of pre-tagged text. For example, the hidden Markov model can be used with the Viterbi algorithm, which relies on statistical models and probabilities to assign part of speech tags. There are transformation-based taggers that combine rule-based and statistical methods in their tagging. And then I mentioned the noisy channel model. This is a conceptual framework that is used in NLP, and we can look at this to illustrate the challenge of part of speech tagging and how these challenges are addressed by statistical taggers, given that within text, there are typos and errors. So commonly we will see typos and errors in texts. And the noisy channel model, I have a link to the Wikipedia page for that here. And you'll find a lot of references for the noisy channel online. But this is a framework that is used in spell checkers. So it's meant to handle and deal with noisy text. So noisy meaning errors and typos. And so you can see how that can contribute to the challenge of POS tagging. On this website, we also have an example that uses the noisy channel model in spelling and provides an example of using that along with a code snippet. And our Python libraries provide us with a lot of methods for part of speech tagging. So some of the part of speech tagging tools can be found in the NLTK library. Some can be found in the spaCy library, which is another natural language processing library that's commonly used. And then TextBlob is another library that we can use. So all of these are going to have tools for part of speech tagging. I linked to just a couple of papers that give an overview of comparing these taggers. So one, the optimal size performance trade-offs, weighing POS tagger models. Link to that paper there, and you can see some accuracy tests results based on different taggers. And then a survey paper from later related to part-of-speech tagging, which is a systematic review of deep learning and machine learning approaches to part-of-speech tagging. So that's another paper I've linked to here that's a good read. To see how the spaCy.io package provides methods that include POS tagging, there's a link to the docs there, which has a quick start for using spaCy. And when you apply spaCy to a text input, part of the output that you get back includes part-of-speech tagging. So you can follow the quick start tutorial there and see what the output looks like. But I also have another code snippet where I wanted to compare the output of NLTK and spaCy in tagging the same sentences. So I start with the same quotes from before. Now I'm importing spaCy. I'm also importing NLTK tag and tokenize. This time I'm not doing sentences, I'm just doing word tokenizing and using POS tag from NLTK to tag the words. For this, you might need to download a spaCy model if you haven't already. So the comment here is directing you to download this spaCy model that we're going to use. And then we load the spaCy model. And so here I've used English Core Web Small model to do the tagging. So I iterate through my quotes and print them out. And then I have a data list where I'm going to store the tokens from word tokenizing, from NLTK tagging, and then from spaCy tags. And finally, I'm going to zip these together, and it looks like there was an indentation error on the copy paste, which I will fix after completing this recording. And then I simply iterate through the results and print them in a tabular form using the very useful Tabulate library in Python, so that I can have a nice side-by-side comparison of the outputs to look at. So this is what the code output looks like. So I've done this for each sentence. So the first sentence, all programs have a desire to be useful. The tokens get split up word by word, followed by the period at the end, and then the different POS tagging models give us a result. So you can flip through and look at these results and see where they are the same and where they might differ. So for this first sentence, it looks like both of the models gave us the same tags for every word. In the next sentence, we can scan through and see the tags that were provided from the two models. And again, we see that both of the models are performing the same and providing the same output. And then finally, the last example. And here, confirming again that we are getting the same output from both of these models. So both of these models are giving us the same POS tags, which we're able to confirm by comparing them side by side. And you will not always necessarily get the same tags depending on which model you use. And that does not necessarily mean one is accurate or one is inaccurate, but there are certain nuances when you look at some words And especially if you consider words that might be misspelled or even improper word use, you can imagine that sometimes a verb might be given the wrong tense or something like that. So while we would hope that we would get the same results for all of the models that we use, that is not necessarily always going to be true. And in addition to that, we here have looked at the Penn tree bank tags. There are also other tag sets that are commonly used. While this one is the most common one that I've seen, there are other tag sets that you'll see being used that have slightly different tags. And as you can see, going through just the English language alone, there's quite a lot of different forms of words. And then, of course, if you're looking at a different language and a different grammar, you're going to see something different, perhaps entirely. So that is an overview of part of speech tagging with some example code to get started in working on that. And this is a common natural language processing task that should become a natural part of the work that you do in NLP.